Cool, I think that's going. Yes, it is. Awesome. All right, so first kind of thing to start with today is a little discussion about if you think that if you have 1 gram of hydrogen, do you have the same number of atoms if you had 1 gram of sodium? So what we're thinking about that, basically we have like a little dish, and I've weighed them out on a scale. And both scales we read 1 gram. That's of my hydrogen, and that's of my sodium. And the question is, would it have the same number of atoms? So we'll do a heads or tails. Heads if you think yes, it would have the same number of atoms. Tails if you think the answer is no, it would not have the same number of atoms. Make a decision. Heads or tails. Come on, heads or tails? Heads is yes, it would have the same number of atoms. Hips for tails, if you don't think it would have the same number of atoms. The answer is they do not have the same number of atoms. And I'll explain why that is the case. But before I do that, I just want to kind of use an analogy first. So I'm glad that you guys have gotten that. Any kind of reasonings to why you guys think that? Yeah.
Something with atomic mass.
Yes, you're right. It has something to do with the atomic mass and the fact that these guys have 2 different atomic masses. So the analogy I like to use is, let's pretend we're at the doctor's office. And at the doctor's office, we can see that there's a scale, and the scale reads 30 kgs. And my question for you is, how many kids does the doctor have in his office right now? Exactly the face that I was hoping for. So you can't answer that question, right? Because you don't know what the mass of the children are. If I have, say, a 7-year-old child, and the child of 7-year-olds are probably around 30 kgs, I would only expect 1 child in that office. However, if I had a toddler that's 1 year old, I would expect them to be about 10 kgs. So if the scale reads 30, I should then have about 3 kids in that office. So that's the thing we have to remember when we're talking about mass, is that we're talking about like the weight of the item. And so we can't use that when we're trying to compare quantities or like amounts. So when we're looking at the periodic table and we're thinking about hydrogen, for example, and we're thinking about sodium, there are 2 numbers that we see on there for each number that's assigned. And hopefully I'm doing the right numbers. I'm just kind of going off the top of my head. All right, so hydrogen has the same number for both of these cases, but sodium has 2 different numbers. What is the smaller number? Do you guys remember? What does the smaller number represent? Atomic number. So what does atomic number tell us? Yeah, number of protons and number of electrons. What's the bigger number represent? What? Everything. So atomic mass. If I'm trying to calculate the atomic mass, what 2 things am I adding together? Protons and the neutrons. Because those are the only things that contribute to the mass of the atom. We don't factor in the electrons because the electrons are super, super tiny. They're like 1/7,000th of a mass of a proton and neutron. So we basically count it as nil. So when it comes to checking the weight of these 2 things, I can't compare 1 gram of hydrogen versus 1 gram of sodium when it comes to number of atoms, because they have vastly different masses, like when we're talking about the kids. So that's kind of something to think about when we are thinking about this new information. We're going to be talking about moles, molecular mass, mass as our kind of 3 things. So that's kind of something I wanted to pull out for you guys. Just as a little side note, I hope I have a periodic table here to show you guys. Remember, we use periodic tables if it was level 3. Okay, here we go. Have you guys ever wondered why some of these numbers are not a whole number? Because we can't have a fraction of a proton or a fraction of a neutron. Any idea of why those are not whole numbers? Done? it's because of something called isotopes. So isotopes are the same element, but they have different masses, and that's just because they have a different number of a different number of neutrons. So that's why it's slightly different. What else did I want to say about that? So yeah, neutron number can vary from atom to atom. This number here is a representative of the average of the different isotopes. So some things are more consistent and have more of the same mass. Others have a little bit of a range. All right, cool. So that kind of gets us started on this idea. I'm just trying to check my notes to see what we had next on our to-do list. Right, I needed to teach you guys about moles and mass, and what I was going to do was to show you guys SciPad pages 8 and 9, so you guys can have an idea of what these calculations look like and how we do this conversion. So let me pass that out, and then we will go back to our notes. Cool. Okay, so let's talk about the number then that we use, or I should actually say the unit that we use to communicate amount when it comes to like number of atoms and things like that. The term that we are using for this is called a mole. The mole is a unit, just like grams and kilograms and things like that. The best way to describe a mole is that it is representative of a number of particles, specifically 6.02 times 10 to the 23rd particles. So when I use this number of atoms, I will then be able to compare hydrogen and sodium to each other. So if I have 1 mole of hydrogen and 1 mole of sodium, then I actually do have the same number of atoms. And if I then wanted to figure out what that number of atoms would be, it would be that big number. Obviously, we're not going to be working with those big numbers because it's really complicated. We simplify it into being a mole. Just like when you say, like, here's a dozen eggs, instead of saying here's 12 eggs. So just a little shorthand for us to kind of communicate things across. I won't do all of these questions, but I will do a variety of them just so you guys can kind of see how this calculation works. So this first one here is just trying to give you an example of how moles work. So when I'm looking at this, if I have 12 grams, I would have 1 mole of calcium. And the reason for that is because when I look at the periodic table and I'm checking calcium, not calcium, carbon, its atomic mass is 12. So if I have 12 grams of it, I then have 1 mole of it. I think it's Angela. Angela, can you turn down your music? Thanks. So if I only have half the amount of mass, how many moles would I have in comparison? Half. So it'd be 0.5. If I had 3, what would that be? 0.25. So you see how that kind of works as a conversion between the two? I actually don't like how this worksheet's organized because it doesn't give you the equation. It gives you the equation on the next page. Do you guys want the equation? Would that help? Okay. So the equation to do this conversion between it is N equals M divided by big M. So what that means is, this is probably the worst equation you're ever going to get because I'm going to say N and M all the time, and there's 2 M's in that equation. So the small n, that is referring to the amount, and that's in moles, is that unit. The little m is referring to mass. Oops, mass. I was getting too excited, I was going to write grams. And that's referring to grams. And then the big M is referring to molecular mass, which is grams per mole. So when you look at the periodic table and we're looking at atomic mass, that number there is giving us the big M. We good so far? All right, so when I was looking at this number, if I was looking at that first page here and I wanted to plug in these values to figure out how many moles I have, what I would do is N equals, let's say, 3 grams divided by the 12 grams per mole. I personally like to write down my units whenever I'm doing any math working for chemistry, because what I can do then is cancel out my units and make sure that I'm doing my calculations correctly. So the grams are canceling with grams, and then I have per mole, which makes it mole. So I've done my equation correctly. And that should be 0.25. And because I don't trust my math brain, I think my calculator's actually finally died. I just put new batteries in it, but I think the actual calculator itself has decided it's had enough of life, which is impressive because I've had it since high school. Let me put it on my phone because I just want to make sure I'm telling you guys the right thing. Yeah, 0.25. Cool. We okay with that? All right, so that's just kind of that bit here. This one here is going in the other direction. So you're converting from from amount to mass. So just be mindful, you're gonna have to rearrange that equation. It's up to you how you want to do that rearranging. You can either enter the numbers first and then rearrange, or you can rearrange beforehand. So n equals little m over big M. Big M is something you should always get because you're going to always get a periodic table. So this is always going to be a known. You're just working with these two numbers here. So if I wanted to rearrange that, I want to get the little m by itself. So remember, we do the opposite to get things moved around. So I would multiply by the big M. And remember, you have to do it on both sides. The big N's cancel out. And then I have little m equals n times the big N when I'm doing that rearranging. So you can do it that way, or, yeah, fix it, blurry, there you go. Or the other option is you can plug in the numbers and rearrange it after the numbers are done. Some people like that better because then they don't have to work with the letters. So if I'm looking at this example, let's not do that one because that one's too easy. Let's look at oxygen, which is 0.5 moles, and the atomic mass is 16. So what I could do is keep the same equation. And I have two choices. I can either plug it in directly like this, m equals 0.5 times 16. So that is 8. Or you can plug it in first and then rearrange. So n equals 0.5. M divided by 16, and then move things around. Like that. Either way is fine. It's whatever your preference is. And if I was to check the units, I would have moles times grams per mole, and then the mole and the mole would cancel out, leaving grams. So I know I've rearranged the equation correctly. So that one is the example for this one here. What did I say it was? 8. Thank you. The other thing to keep in mind is that if you have any molecules, the atomic mass then is equal to the sum of those atoms. So if I'm looking at something like methane here, which is that carbon and 4 hydrogens, the atomic number of carbon is 12. And then I would add the hydrogens. Atomic mass of hydrogen is 1, and I have 4 of them. So I'd multiply that by 4 to get my total number. So it'd be 12 plus 4, so that would be 16 grams per mole if I was looking at a full molecule. So just kind of keep that in mind when you're looking at it. I think that's mostly kind of everything. I'll give you guys some time to practice that. On the other sheet here is the same thing. It's just, this is why I don't like these two sheets, because I feel like they didn't order it very well. You can have, again, some more practice doing that conversion back and forth. And also they have some questions down here. So first you need to figure out the atomic mass of the compound, and then you can use the equation. Do you guys want to see an example of that? I'm seeing head shaking. Okay. So if I was doing these questions here, the first thing I need to do is I need to figure out the atomic mass of the calcium. So calcium, I have the 1 calcium atom. And if I look at my periodic table, which I'm now realizing I should have probably printed out for you guys. So calcium is 40. I only have 1 of them. And then I have my chlorine, and I have 2 of them. So chlorine, when I look at the periodic table, is 35.5. I'll use that number. And then I add all that up to get my atomic mass. So that's 35.5 times 2 is 71, plus the 40 is 111 grams per mole. So that's what the atomic mass would be for that compound. And then what I want to do then is figure out the moles of 40 grams of calcium chloride. So I'm using that N equals little m over big M. So N is equal to 40 grams divided by the 111 grams per mole. And then I can figure out that this is 0.36 moles, like that. So this one's similar to the stuff on the previous page. We're just combining multiple steps together. We okay? Okay. So what I will now do is I will give you guys some time to work on these 2 pages. I don't want to give you endless amounts of time because I do want to move on and give you guys the concentration equation as well. So yeah, that's the plan. Oh, perfect timing. All right. So to talk about the grams per liter versus moles per liter, it is far more useful for me to have the unit mole than have the unit grams. And the reason why is because moles allows me to compare stuff to each other. The main thing we got to keep in mind is the equations here. And these equations are all referring to how much of, say, for example, hydrochloric acid do you need to neutralize the sodium hydroxide. These either have numbers in front or they don't have numbers in front. If they don't have numbers in front, you assume 1 mole. So what this is telling me is that I need 1 mole of hydrochloric acid and 1 mole of sodium hydroxide in order to neutralize each other. So that talks about amount, and that's far more useful. If I was comparing grams to grams, I would have 2 different numbers because they have 2 different masses. So that's the reason why I would want to work in moles versus grams for all of my kind of work that I'm doing. A better example of an equation just to talk about why we need the mole number is, let's say, for example, we had sulfuric acid plus sodium hydroxide. I'm just gonna, so 4 plus H2O. So again, you can see that there are numbers that are used as ratios in the equation. And what this is telling me is for every 1 mole of sulfuric acid that I have, I need twice as much sodium hydroxide to neutralize it. So that's why we want to use the value of moles. So do kind of keep that in mind. We still have to work with mass in grams though, because when we go to a scale, the unit in the scale is grams. So that's why you have to do that conversion. If you are wondering why don't we have lab equipment that then measures things in moles, the reason why is because we'd have to then input each time we were measuring something the chemical that we're using, so that way the machine could do the conversion for us. It's a lot easier for humans just to do it themselves and then just have one equipment to do all the measuring of the mass. This is probably the most common equation I was using in my master's degree because I need to figure out how much of my drugs I need to measure out to then get my amounts correct. The next thing that we then have to do is think about concentration. So for this standard, what you guys are going to be doing is you have a known concentration of sodium hydroxide, and I'm asking you to find the unknown concentration of a household acid. So be it, for example, I think it's, I can't remember the acid, like citric acid in orange juice, as an example. Again, we have another equation. In this case, we're talking about concentration, and concentration is equal to whatever amount we have in moles divided by the volume of the solution that you are dissolving it into. Keep in mind that the volume has to be in the unit of liters, so we always talk about moles per liter as our unit. So watch out, because with our titration topic, you're measuring in milliliters, and you're going to have to convert it into liters. Do you guys know how to do that conversion? Sort of? No? How many milliliters are in a liter? 1,000. So I would then divide by 1,000. So 1,000 milliliters is equal to 1 liter. So if you have to do any conversion between milliliters to liters, that's how you would do it. All right, let me do some examples for you guys, just so you know how to fill in this sheet. So we have the formula for sodium carbonate. We have the mass. First thing I need to do is figure out the molecular mass. Again, we use the periodic table, which I forgot to print for you guys, and I think my periodic table is over by Lucy. Calcium is 23 as the atomic number. How many, sodium is 23. How many do I have? 2. So I do 23 times 2 as my first step. Let me get my calculator because I can't do mental math. So 23 times 2 is 46. And then I have to add my carbon. So what's carbon? C, 12. And then I have oxygen, which is 16. And how many do I have? 3. So that means I have to times the 16 by 3. So my mass is 106. Or my molecular mass, I should say. You're using the same equation from previous. So we have N equals little m divided by big M. So I'm going to do 2 divided by 106. And I get 0.01. I'm going to round it up to 9. And then the last step here, when I want to find concentration, I take my amount and divide it by the volume. In this case, my volume is 0.1. So I'm dividing that number by 0.1. Divide by 0.1. And so I get my concentration to be that number there. So 0.189 moles per liter. You should have 3 significant units when you're doing chemistry. So 1, 2, 3. We'll do significant units when we start doing the part B. I just wanted to point out to you guys. And then these here, you are working in the other direction. So just keep in mind you're rearranging the equation to find N. So in this case, you would have N equals C times V. So I've just rearranged it to solve for N. If you guys want to use the triangle, you can, but like honestly, I really hate it because I don't think you're actually learning how to do the skill set, and it only works for really basic equations like this. But yeah, if we wanted to find N, it would be C times V. Cool. All right. I will give you guys the rest of the period to work on this. Does that sound like a good plan? There is a GIM kit we can play, but I figured you guys probably want some practice before we play the GIM kit, right? Okay. Cool. I think that's basically all of it. Yeah. All right. I'll leave you guys to work. We have 10 minutes left. Do you guys want to have your preferred activity time today, or continue to save it until we have one of our, save it? Rather just work to the end of the bell? Okay.